Dear friends, today in this session we are going to learn about the polar moment of inertia for the solid circular section and hollow circular section, how to determine its least radius of gyration. With this, the moment of inertia course will be completed. Hence, I request your attention for this class, which involves all the theorems and formulas. In the earlier session, we are determined the moment of inertia and least radius of gyration for unsymmetrical jet section and built-up sections using parallaxis theorem. In that, we are also seeing the channel sections and how to arrange the uh, angular sections to increase the moment of inertia for the better bending strength. So in this session, you will be able to know about determining the polar moment of inertia and least radius of gyration for solid and hollow circular sections, applying perpendicular axis theorem also. And we will also see the moment of inertia for the shapes including hollow portions, how we have to determine the moment of inertia for shapes including hollow portions. That we are procedure will be the same as we followed in the centroid, in which we are also done the finding of the centroid for the hollow portions having the shapes. So for that we are taking the area as negative, and we will do the same process here also, but in the case of area we are going to deduct the moment of inertia's values from the summation of all the values. And at the end we will see that all the moment of inertias of the useful for your EZ point of view, and as well as for the your academic point of view. The list has been provided for your easy reference to by heart the same for your competitive exams. In the previous of the 4 or 5 previous sessions, we are already discussed about the how to determine the moment of inertia of a circle about its centroid. Being it has been categorized under separate topic, so we are presenting for the same to you, and we will extend this topic for the problematic area too also. So for that the derivation we are derived for the formulae of the moment of inertia of a circle about the centroid by taking a differential area as a d rho into 2 pi rho as a differential elemental area, which has the boundary limits from the 0 to up to r. So this differential element area has been have the boundary values from 0 to r. So by using the integration method or the first principle, you can derive this formula for the circular section. For the circular section, the polar moment of inertia is Iz is equal to Ip, that is polar, that is also known as J. So use those formulas for the integration principle of the second moment of area, that is equal to rho square dA. Then substitute the rho value as a uh, given values. Then rho has been a value of 0 to r, and differential element area is 2 pi rho d rho. So using by substituting all those relevant data and integrating with that, you will obtain the 2 pi root to the power of 4 by r, and then substitute the limits. Then the polar momentum of inertia of a solid circular section is pi r to the power of 4 by 2. So this can also be written in the dia also. Then it would be pi d to the power of 4 by 32. So this is the your derivation of the polar moment of inertia of a circular section. So for the using the perpendicular axis theorem, you can also define the moment of inertia of the solid circular section as the perpendicular axis theorem says that Izz is equal to Ix plus Iy. So Izz can also be represented as polar moment of inertia Ip. So therefore, it is the sum of the moment of inertia about the centroidal axis. Hence, Ix plus Iy has been as the centroidal moments about the circular section centroid. So you know that being the circle is infinite symmetry, hence it can be taken as Ixx equal to Iyy. So it has been represented as Ixx equal to Iyy. Therefore, 2Ixx or 2Iyy or 2I is equal to j. Therefore, substitute this value into this equation to get the Ixx or Iyy value of a solid circular section. So remember, the solid circular section moment of inertia is founded from the using the first integral principle and perpendicular axis theorem. Now for this case, this is the scenario. Therefore 2I is equal to pi d to the power of by 32, which has been derived in the previous slide. So the same has been used for the I is equal to pi to the power of 4 by 64, because it is to be multiplied with this 2, then you will get the 64. When d has been converted into r, so it would be pi r to the power of 4 by 4. So with this knowledge of the moment of inertia or polar momentum of inertia of a solid circular section, the same theme can be expanded to the hollow circular too. In this particular case, we will use the basics of the solid circular section formulas to determine the moment of inertia of a hollow circle, which can be termed as for a 3D it might be a tube. We can also call it as a pipe or tube like that. So the circular section is symmetric about both the centroidal axis. Adopt the procedure of determination of moment of inertia for hollow rectangle. The hollow circle consists of two circles. One is outer circle and another is inner circle. The outer circle is this one is the outer circle. This is the inner circle. So we have the two radiuses or two dias for the same thing. We know that for the each circle, the moment of inertia is pi d to the power of 4 by 64 or pi r to the power of 4 by 4 for each circle. So we are understood that there are two circles, one is outer and another one is inner, makes the hollow circular section. So we will notate the same thing. The outer circle has d naught and diameter or radius is r naught. The diameter of inner circle is denoted as di and the radius of is also denoted as ri. Being It is bisymmetric or infinite symmetry of the circle. The x-axis and y-axis will be the same. uh, x-axis and y-axis can be gives the same values. Hence, the moment of inertia about the x-axis equal to moment of inertia about the y. So, the formula of the moment of inertia will be used for to solve the hollow circular section. Let give the same notations and follow the formula of the Ixx. So simply we can say that a big circle and a small circle, if the small circle is detected from the big circle, you will obtain the hollow circle. So hence the Ixx values of the small circle, if you deducted from the big circle, you will obtain the moment of inertia of the hollow circle. It is such a simple procedure. So do the same thing. The outer circle Ixx value has been minused into the inner circle to get the moment of inertia of a hollow circle. Now the moment of inertia of hollow circle is pi by 64 times of the d to the power of 4 minus di whole to the power of 4. So the same thing can also be written in terms of the radius. Just replace the 64 as 4, therefore pi by 4 r to the power of 4 minus ri to the power of 4. So use the notations of the outer and inner radiuses or dias. Frequently in the competitive exams they will ask the hollow circular questions as it is required to memorization and concept. Now we will move into the problematic session of this knowledge. Let us determine the polar moment of inertia about its centroid of a circle having 50 mm radius. So he has given the radius is 50 mm. The radius is 50 mm. Hence radius of solid circle is 50 mm and diameter is it is twice of the radius, hence it is 100 mm. For the moment of inertia of a circle section or solid circular section, this is equal to the all the Ixx or Iyy are equal to a single notation moment of inertia, that is equal to pi d to the power of 4 by 64 or pi r to the power of 4 by 4. Substitute the values of the radius or diameter. So the I value is 4908738.52 mm to the power of 4. But in the question they are asked about the polar moment of inertia. For this, use the perpendicular axis theorem. For the perpendicular axis theorem, Ij or Ip or Iz is equal to Ixx plus Iyy. That is nothing but 2 times of the I. Therefore, we need to multiply this value. Then Izz is equal to 2I. Therefore, 2 times of the I value. So this is the principal polar moment of inertia of a solid circular section. It is understood that Izz is equal to being 2I times. Hence, you can use the direct formula pi r to the power of 4 by 2. Therefore, r substitute the r value, you will get the same value in this formula. Or it can be in terms of the d, it is pi d to the power of 4 by 32. Simply, you can avoid the procedure simply just knowing the formula within 1 second. I can say within 50 seconds you can obtain this answer. Instead of having this much of procedure, you can avoid by simply substituting this formula. Simply substitute this formula to get the easy value. Similarly, determine the polar moment of inertia and the least radius of gyration for hollow circular tube having outer radius is 150 mm and thickness of tube is 20 mm. So in this particular case, he has given two dias or two radiuses indirectly. So for the hollow circular tube, he has given a outer radius is 150 mm and thickness of tube is 20 mm. Then substitute the values to obtain the polar moment of inertia. Let us give the notations of the each circle. The outer circle radius is R0, that is equal to 150 mm. Outer diameter is 2R0, that is equal to 300 mm. And radius of inner circle is can be obtained by deducting the thickness of the tube. Therefore, 150 minus 20 to get the radius of the inner circle. So, if the tube is like this, let us say, so this is the thickness. The thickness is given from this point to this point is 20 mm. This is the 20 mm. Hence, we need to minus this 20 mm to get the radius inner side. So from this point up to this point, it is 150. Now they are asking what is the radius of this position. So for this, 150 minus 20 up to this point it is 150. Therefore 150 minus 20 you will get the 130. Right? Then to get the inner diameter 2Ri is equal to 260 mm. The moment of inertia of a tube is similar to the hollow circular section, hence the same formula is holds good. Therefore, moment of inertia is equal to Ixx is equal to Iyy. If you know the diameter, you can give the formula in terms of the diameter. If you know the radius, you can formula the value in terms of the radius. Therefore, Ixx or Iyy of the hollow circular section is equal to I divided by 64 and whole to be multiplied with outer dia to the power of 4 minus inner dia to the power of 4. Similarly with the radius, substitute the values of the outer dia and inner dia or outer dia, outer radius or inner radius to obtain the value of the Ixx and Iy value. So the moment of inertia of a hollow circle is, with the given data, it is 173290,250.8 mm to the power of 4. Then polar moment of inertia can be obtained from the perpendicular equation. So that is Izz is equal to Ix plus Iy. So that is nothing but 2 times of the moment of inertia. Hence, substitute the values to get the same. So, perpendicular axis theorem has been used to find the polar moment of inertia. And you can also minimize the this entire procedure by using the simple direct formulas. This is the formula of the polar moment of inertia of a hollow circular section. Use this formula directly to obtain the polar momentum of inertia. Within 1 minute, you can give the answer in the competitive exams. Remember, the I value for this hollow circular section is pi by 64 times of the differences of those dias to the power of 4, whereas the polar moment of inertia for the hollow circular section is pi by 32. That is the only change, pi by 32. For normal I-axis it is pi by 64. So just that value you can change and you will obtain the polar moment of inertia of a hollow circular section or a tube or pipe. So use this simple procedure and remember this formula for the competitive exam purpose. Therefore, Ij is equal to 346580,501.5 mm to the power of 4. Now they are asked the question, what is the polar, polar moment of inertia and least radius of gyration? For this, you have to use the formula of Rxx or Ryy. For the Rxx or Ryy, you should substitute the value of moment of inertia and areas. Hence, radius of gyration is equal to square root of I by A, being Ixx is equal to I by Y, and substitute the I value, and area of the hollow section, hollow circular section is pi by 4 d naught square minus di square. So substitute the values of the outer dia or inner dia in the formula to get the area. The area of the hollow circular section is 17592.92 mm square. After substituting those I value and area value in the formula, you are obtain the value of 99.25 mm as the radius of gyration. For the hollow circular sections or solid circular sections, the Rxx is equal to Ryy. Hence, it is a minimum value can be readed. Therefore, 99.25 mm is the least radius of gyration, which is equivalent to the Rx and Ryy. So this is the procedure for the determination of moment of inertia and polar moment of inertia and the least radius of gyration for the solid circular section and hollow circular section. Now with this knowledge we can move into the another typical level of the question formation. So for the competitive exam point of view, you can use this formula. For the fraction of seconds you can obtain the answer of the least radius of gyration. So this is the least radius of gyration formula for the hollow circular section. So memorize this one for your success in the exams. Therefore, radius of gyration is equal to square root of summation of squares of the dias of inner and outer divided by 4. So use this formula to solve the moment of that is radius of gyration for the hollow circular section. So it is only 1 minute time to solve the problem. Now move into the atypical level of the question. Determine the ratio of outer diameter of a hollow circular to the solid circular diameter when the least radius of the gyration For hollow circular tube having inner radius is 100 mm and the solid circular section having radius is 150 mm are equal, and that means he is asking about the ratio of outer diameter of hollow circular section, ratio of outer diameter of solid circular section and solid hollow to the circular section. That means if this is a normal circle and he wants that this is the hollow circle. So this is a solid, this is the solid section and this one is hollow section. For the solid section and hollow circular section, he is asking about the ratio of this D, and for this hollow circular section, this is will be the outer dia D naught. This is the outer dia. Now he is asking about the hollow to, that means D naught divided by D. So he is asking about what is the ratio of D naught by D. In this particular question, he is asking the ratio of outer diameter of hollow circular section to the solid circular diameter. So that ratio is asking when the least radius of gyration of hollow circular tube having so and so are with the equal. That means both the radius of gyrations of the solid section and hollow circular section, that means radius of gyration Rs of the solid is equal to radius of gyration of the hollow. So this is the condition he has given for us to determine the ratio. So he has given radius of gyration of solid circular section is equal to the radius of hollow circular section when d naught by d should be found out. So for this he has given some values of the radiuses. The circular tube having the inner radius is 100 mm. So inner radius is given 100 mm. Right? Therefore inner diameter is 200 mm. And the solid circular section having the radius is 150 mm. So solid circular section is given 150 mm. Note down, he has not given the outer radius d naught value. So in order to find out this, we need to find the d naught value, and after that we have to find the ratio of the d naught by d. So in order to find out the d naught value, he has given the condition of least radius of gyration for the solid circular section and the hollow circular sections are equal. That is the condition he has given to find the d naught value. So for that, let us determine the radius of gyration of the solid circular section and hollow circular section, then equate that to get the outer diameter, and thereafter to obtain the ratio. So for this, the least radius of gyration of a tube or a hollow circular section is Rxx equal to Ryy square root of capital D square plus small d square whole divided by 4. Use that formula to determine the Rxx of the hollow circular section. And similarly for the solid circular section, it is simply Rxx equal to Ryy d by 4 or r by 2. Use that formula and equate them. Therefore, radius of gyration of the solid section is equal to hollow section, that is given in the problem. So this is the values. Then substitute that one. Substitute the values to obtain the d naught value. D is already given 300, that is the solid diameter, circular, and whereas the inner diameter of the circular section is 100, substitute that one. A small correction. So the radius of the dia is 50 mm of the inner circle. Therefore, this would be 100 mm. This would be the 100 mm. Therefore, use that value for the solution. Therefore, this is the 100 mm. Then obtain this value of the D naught of the outer dia. By squaring on both sides, you will obtain the D naught value by simplification. Then substitute that value D naught by D, as the in question they are asked about the ratio. So that would be 282.84, which is the D naught value, and the outer dia or the solid circular section is 300 mm. Then this is the ratio. Now with this, we are moving to the hollow portions of the circular sections also for determining the moment of inertia about the centroidal x-axis. So of the given figure, the given figure is hut. So in this he has mentioned that the door portion considered as hollow. So this is the door portion. Here it is the door portion which is considered as hollow of the hut. So total hut, in this one the door portion has to be considered as hollow. So this is the hollow area. So let us to be removed. So the dimensions given for the width of the hut is 200 mm and the roof of the hut is 250 mm height. So from this point to this point is 250 and from this point it is 400. Whereas the rectangle portion is there up to this portion, it is 200, and the semicircular portion, here it is a semicircular portion is there, so which is the semicircular portion is having a height of 50, so which is nothing but radius of the semicircle, which is nothing but radius of semicircle. So in this one you can find the four parts. The first part is, this is the one, and the total rectangle portion, this is entire 400 by this total dimension of the 200. 400 by 200 is the second rectangle portion, and this one is the third. Up to this portion, this is the third one, and semicircle is fourth one. So we have the total four parts. Total four parts. So by considering these all total four parts, you can determine the moment of inertia of this hut by the centroidal axis only. In this problem, they are asked only x-axis. So you need to find the centroidal moment of inertia about the x-axis of the whole figure. The same procedure holds good for the centroidal of the y-axis also, but in the question they are asked only centroidal x-axis. So in this they are also mentioned that the door portion is considered as hollow. So this portion is totally hollow portion. So we need to detect the same thing for the centroidal calculation and for the moment of inertia calculation also. Let us do the as per the routine practice. We have to identify the symmetrical axis, is there available or not. It is understood that it is not the symmetry. Is it symmetry? If I draw a line about at any point, is it symmetry? No, it is not symmetry. Not symmetry about x axis. Hence use the analytical method. So use analytical method to find the centroid. So first step, what we need to find the centroid. Then second step, individual I-axis values. Then third one, use the parallel axis theorem. Then find the total I-axis, total I value. For that, deduct the hollow portions is required. Deduction of hollow portions is required. So let us go for the procedure. So first is to determine the centroid. To determine the centroid, as per the notation, 1, 2, 3 and 4 is the door semicircle is the fourth point. So this one I can say that is the fourth point. So roof has been is an isosceles triangle, hence use the formula of BH for the area, and y bar has been taken from the bottom, and let us say like this, the figure is like this. So being this is your figure of the given hut, just a rough figure I am drawing for your convenience. So this red portion has to be deducted area. This has to be a deducted area. So this is the portion they are given. So for this, from this point it will be the 400, up to this point it is a 400, and beyond this point it is a 250. This is 250. Hence 400 plus 250 by 3, h by 3. It is nothing but h by 3. This is h by 3. Right? So 400 plus h by 3. By using this value, so this is 525 for the isosceles triangle YN. And for the wall portion, this is only 400 by 2. So the same has been used. So this total distance is 200. That is already we know that this is 200. Therefore 200 by 400 is the wall. And for this y bar, 400 by 2. Why we are calculating the y? Because we need to find the moment of inertia about the x-axis. For that, we require the y bar value. So that's why we are calculating all the y values. Similarly, for the door rectangle is, this is the 100, this distance is 100, and this height is 200. So that is the area, which is a negative area, which is to be deducted. This area to be deducted, hence it is a negative. It is a negative. So negative symbol has been given for the areas of the to be deducted. So you can also see the values in the negative. So similarly follow the procedure. For the semicircular area, this is pi r square by 2 is the area, and the semicircular centroid is 4r by 3 for the semicircular. For the semicircular, the centroid is 4r by 3 pi. Here it will be 4r by 3 pi. So 4r by 3 pi is the semicircular area, centroid of the pi bar. So that formula has been used here, 4r by 3 pi, and it is at a rectangle of the door which is 200. From this point to this point it is 200. So the same thing has been added here for the finding the centroid of the semicircular. So after substituting all the values, you are obtained the AY value of the then summation by deducting the hollow areas of the door portion. Then the Y bar is came out 323.86. So generally it would be above the door area. So here it would be the 323 point. This would be 323.86 is the Y bar. Now it is observed that for the determination of Ixx, we have to check whether the need of the parallaxis theorem is required or not. For that, use the y values y1, y2, y3 and check with the y bar whether it is useful or not. So here total y1 values are up to y4. Therefore, y bar values have been checked with that. Y bar is 323.86, but y1 is 525. Y1 is located here and y bar is located here. This is the y bar. So this distance is required for us and to employ the parallaxis theorem. Even for the y2 it is 200. Therefore, y2 is located somewhere here. So y2 is located here. And similarly, we require this distance as d2. And y3 is located somewhere here. Y3 is a rectangle portion here. For this is the line. So we require the d3 from this point to this point, whereas the y4 221.22, so it is nearly about this point. This is the point. So this is the d4 point. So with this we have to find the d1, d2, d3, d4 values to substitute in the parallaxis theorem, AD square. So these are the values we are obtained for the d1, d2, d3, all the values. So substitute in the parallaxis theorem. So the d1 is equal to y bar minus y1, and d2 is equal to y bar minus y2, d3 equal to y bar minus y3. Like that, all the values you need to substitute in the values to get the Ixx of the entire hut. For that, tabulate the values. Being hut portion of the roof is isosceles triangle, IXC is equal to BHQ by 36, whereas the wall is a rectangle portion, BHQ by 12 is the IXC. Door is a rectangle which is a negative portion. So you please see that here we have given a negative value for the door of portions of the rectangle and semicircle. For the semicircle, the formula is for the IXA 0.1098 r to the power of 4. Use that formula and obtain the IXC values. Areas are taken from the centroid table and used for the AD square multiplication. The D values are should be squared to obtain the accurate values and substitute all those values. IXX has been summarized to get the total shape IXX value, that is 2454830090 mm to the power of 4. So in this procedure we are also seeing that how the moment of inertia of the deducted portions to be taken as negative and the remaining are taken as positive. Right? So this is the concept of the hollow portions in the given shape to obtain the moment of inertia. So with this we are from so many days we are discussing about the moment of inertia and centroid. So let us give the conclusion of those two chapters by understanding the formulas and memorizing of the sections of the basic shapes. So these formulas are taken from the standard textbook, which is written by the Gare and Timoshenko, which is a standard reference book. So please purchase if it is available to you, which gives a wide knowledge about the how to deal with the mechanics of solid subject. Let us know these values. So earlier we are also discussed and derived these formulas, but I wanted to make you these reference tables are keep with you to by heart the values to success in the competitive exams. Here in this table they are given the area of the each shape and its x bar and y bar values and the axis where they are taken the axis reference they are given to understood from this is the point, then what will be the y bar and what will be the x bar values they are mentioned, and ix value, iy values of this about the centroid bhq by 12, that is we are already known for this one, and leave this formula. This is not in your syllabus. It is a product of the ixx and iyy. That is a separate methodology how to do that. So let leave that. It is an integration portion is to be changed for that. IP, that is that you know that just adding up ix and iy you will get the IP. Similarly, if the origin is at the corner, that means like this, the axis is like this, then what would be? It is nothing but a triangle formula. Right? So similarly for the triangles also, there are different triangle shapes are given. For the standard triangle, this is the formulas we are going to use. We know that already Ix equal to BHQ by 36. Right? And Iyy also he has given the formula, right? Which is we are not derived, but standard cases only we are derived, like isosceles triangle we are derived, and the origin if it is at the O, then how the values would be changing. So Ix now will be going to be changed as Ix equal to BHQ by 12. If the axis of consideration has been going to change, the Ix value is going to be changed and Iy value is also going to be changed. Similarly, IBB value has been how the value is coming at the base. So this is also be given in this one. And we derived the IBB value of the isosceles triangle in the earlier sessions, that is BH cube by 12, and Ixx and Iyy values are also be derived for our convenient. It is also be tabulated here. And right angle triangle at the origin of axis at centroid, right angle triangle origin at the axis is at angle vertex. That means we need to employ the parallel axis theorem. If the origin is taken here, so as we know this value, so it is a D. So we apply this formula, it is going to be changed. So increases the value. If the distance from the centroid, if you are going, so moment of inertia will obviously increases. You can see at this point it is only BH cube by 36, whereas up at this point the BH cube is by 12, that is the variation. So it is a higher value when compared to this value. So this is the comparison of the origins if you are taken. And similarly for the trapezium case also, directly they are given the areas and y bar and ix ibb values. So to memorize this one for the competitive exams. And for the circle also they are mentioned here, ix and iy values and polar moment of inertia values. So this is also differential values for us. Number of times they will ask. And circular rings are also being, ring is different, so circular rings are also be given here, how the values are being taken with the thickness. So this can be also nothing but your hollow circular section, but here they are giving the thickness in terms of the radiuses. And for the semicircular, so this is the formula I used in the problem. This is 0.1098 r to the power of 4. I referred many things from the internet also, but for the semicircular, Ix value is not given rightly, but in this book they are given a good value. Iyy, somebody generally what they will do, that they will confuse you. Ixx will also taken as pi r to the power of 4 by 8, so it is not the case. Ix is 0.1098 r to the power of 4 and Iy is equal to pi r to the power of 4 by 8. So please memorize these values for your better accuracy. So for the quarter circular also the values are given. So these all are useful for you for your preparations. And similar circular sector, circular segment, circle with removed portions, and ellipse. Ellipse is sometimes they will ask in the exams. Its area is pi AB and Ix value and Iy value, and similarly Ip value. So this is several times they are asked this one. So memorize this one also. Along this one, this parabolic generally comes for the in next semester you will deal with the parabolas for the moment of that bending moment calculations, deflection calculations. You are required these values. For that I also provided the same for your reference. This is certainly not required, but however these two are also be given for your future reference. In any competitive exam they can ask these also. So with this, we are came across the hollow circular sections and built up sections and everything. We are came across all these problems. So try your own with the standard procedure and uh, get the uh, correctness of the values. For more practice, do and do uh, to get the success in competitive exams. So in this session, we are discussed about the determination of polar moment of inertia and least radius of gyration for solid and hollow circular section, applying perpendicular axis theorem, and we are also determining the moment of inertia for shapes including hollow portions, and we refer the standard formulas of the moment of inertia and centroids of different sections, how the axis is going to be um, change the your value of moment of inertia parallel to the centroidal axis. So we are also discussed all these content. With this, we are ending the this course of the moment of inertia. Thank you. Subcourse.